Okay, now in the case where c squared minus 4km equals 0, turns out that that occurs. If that occurs, your discriminant is 0, and you can see easily that that leads to repeated roots. The repeated root is negative c over 2m, and that leads to the function, first of all, b e to the negative c over 2mt, but if you want to get a general solution to the homogeneous equation, you're going to also have to try solution c t e to the negative c over 2m times t. Now let's see what this solution might look like. Okay, and let's do that in the context of the previous solutions. Okay, c squared minus 4km is less than 0. You recall that gives us negative discriminant. We're going to end up then with a multiple of e to the negative I times, well, it's going to be square root of 4km minus c squared t, giving us in general a sine or cosine of this square root times t plus some theta or initial angle theta naught. And then that's times e to the negative ct over 2m. How does that solution behave? Well, e to the negative ct over 2m, that would be, let's say this curve, is a decreasing exponential, asymptotic to the axis. The sine or cosine term, of course, is oscillatory. The amplitude of this oscillation, if you can use the word amplitude a bit loosely, can be at most well, the amplitude at any, let me not say that because this sine function intersects this a little bit to the right of the point where the sine function maximizes. So I was going to say something about that, but I'm just not going to. You basically have an oscillatory system where the amplitude decreases exponentially because of this being multiplied by this. There are a couple of finer points there that I'm just going to skip over. You can deal with. You can take derivatives, figure out where the actual maximum value of this function is going to occur. But down here, now, if we take the second case where c squared minus 4km is greater than 0, discriminant greater than 0, you get two real solutions. One with a slower exponential decay, another with a faster exponential decay, but both exponentials approaching 0 as an asymptote. Now, you could, this could correspond to, let's say, one exponential approaching 0 quickly, that would be this one, and another approaching 0 more slowly. I'm not sure I really got that. Well, yeah, this one approaches more slowly. You can think about how those would combine. Okay, and this, of course, would correspond to B being a positive, C being a negative. So if you combine these, you still get something that looks kind of like this, but it's not purely an exponential. And we can talk a little bit more about the physical meaning of those two solutions, and we probably will. But for now, let's contrast that with the function we get for the discriminant equal to 0. Now, I'm saying that if the discriminant is 0, we can get this sort of solution. Okay, here we imagine releasing the pendulum and allowing it to just oscillate back. It approaches the equilibrium position as an asymptote, and it can't overshoot the equilibrium position. Whichever side of equilibrium it happens to be on, it's not going to go past the equilibrium position. Whereas in this case, we can overshoot equilibrium, and that leads us to this sort of solution. Now, we can only overshoot once, and then that's it. Now, how does that sort of solution occur? Well, the TE to the negative C over 2M T is going to have a graph that looks like this, and you can easily analyze that. You just multiply an exponential function by a linear function, and you see that when the linear function is 0, you're going to get 0. The linear function is 0 here. But then the linear function increases as the exponential decreases. The exponential will overpower the linear solution in the sense that it'll drive the solution to zero in a way that you should understand from pre-calculus and even better from calculus. Of course, you can analyze it using the calculus, and you're going to have a maximum somewhere in here. Now, of course, if you do a first derivative test, you can figure out where the maximum is, and you can verify this, but we're not going to go into those details. So that when you add two functions like this, well, if this function is steep enough downhill and this one is a little different, if this negative, okay, if this function, if you have a negative multiple of this function, you can get this added to this, and it's easy to see that if this is steep enough in the negative, you can drive the function, the sum, negative before it comes back and approaches equilibrium from below. And this corresponds to a pendulum or an oscillator overshooting equilibrium, then gradually coming back.